There's a question in mathematics that has a peculiar way of dividing people into two camps, and it goes like this. Is 0.999, that's zero point 0.9 repeating forever, equal to 1? Or is it something slightly less than 1, perhaps infinitely close but never quite reaching it? At first glance, your intuition might scream that these can't possibly be the same. How can something with nines stretching out forever equal exactly 1? Now, what makes this question so fascinating isn't just the answer, which we should say up front, is that they are indeed equal, but rather how the journey to understanding this equality illuminates some beautiful and subtle aspects of what infinite decimals actually mean. Today, we want to walk through not just one, but 5 different ways to see why this equality holds true. And more importantly, we want to address the very natural, intuitive resistance you might feel to this idea. Because that resistance, it's not just reasonable, it's instructive. Before we dive into proofs, we need to be absolutely clear about what we mean when we write something like 0.9999. This isn't just notation, it's a precise mathematical definition. When we write 0.999, we're not describing a process that's still happening. We're giving a name to a specific real number. These 3 dots tell us the pattern continues forever. But more importantly, they tell us we're dealing with a completed mathematical object, not an ongoing process. Formally, we define 0.999 as the limit of partial sums. This isn't arbitrary. It's how all infinite decimals are defined in mathematics. This definition symbol means we're establishing what 0.9999 represents as a mathematical object. Every infinite decimal expansion gets its meaning this way. We can express this process as an infinite series. 0.9 plus 0.09 plus 0.009 plus 0.09, and so on. Each term gets 10 times smaller than the previous one. Let's see how these partial sums behave. The first partial sum is just 0.9. The second partial sum is 0.99. The third is 0.999. As n approaches infinity, what do these partial sums approach? But here's the crucial shift in perspective. 0.9999 doesn't represent a process that's still happening. It represents the end result of an infinite process. This is similar to how, when we write p, we don't mean the process of calculating more and more digits of pi. We mean the specific, well-defined number that all those calculations are approaching. The same is true for 0.99. Mathematically, 0.999 is defined as the limit of these partial sums as n approaches infinity. Here's an approach that connects to what you learned in elementary school, but we need to be careful about our assumptions. Let's start with a fact that can be rigorously proven. What's 1/3 as a decimal? Through the algorithm of long division, a completely rigorous procedure, we can verify that 1/3 equals 0.333. This isn't assuming anything about infinite decimals, it's deriving the result. The long division process never terminates, giving us a repeating decimal. Importantly, we can prove this representation using the same limit definition we established earlier. What's 3 times 1 to 3? Obviously, 3 times 1 to 3 equals 1. That's basic arithmetic. But we also know that 1 to 3 equals 0.333, so we can write this as 3 times 0.333. So what is 3 times 0.333? Let's think about this digit by digit. 3 times 0.3 equals 0.9. 3 times 0.03 equals 0.09. 3 times 0.003 equals 0.09. The pattern is clear. 3 times 3 equals 9 in every decimal place. Therefore, 3 times 0.333 equals 0.999. But we also established that 3 times 1 to 3 equals 1. Therefore, 0.9999 must equal 1. Now, you might ask, How do we know that multiplying 0.333 by 3 really gives 0.999? This works because multiplication distributes over convergent infinite series, a property we can prove rigorously using limit theorems. Now that we've established what 0.9999 means as a mathematical object, let's start with what might be the most elegant argument. We'll set x equal to 0.999. Remember, by our definition, this means x equals the limit of the sequence 0.9, 0.99, 0.999, and so on. Now, here's the key insight. What happens when we multiply both sides by 10? For infinite decimals, this operation is well defined because limits preserve algebraic operations. 10 times 0.999 equals 9.999. Here's the key insight. Notice that 9.9999 can be written differently. We can decompose 9.9999 as 9 plus 0.999. But remember, we defined x to be exactly 0.999. So we can substitute x back in. This gives us 10x equals 9 plus x. Now we have a simple algebraic equation. Let's subtract x from both sides. Subtracting x from both sides. This simplifies to 9x equals 9. Dividing both sides by 9. We get x equals 9 over 9, which equals 1. And since x was defined as 0.9999, we have our result. 0.999 equals 1. Now, you might feel like there's something fishy going on here. Are we allowed to manipulate infinite decimals like finite ones? The answer is yes, and here's why. This works because of a fundamental theorem about limits. If a sequence converges to L, then multiplying each term by a constant gives a sequence that converges to that constant times L. When we write 9.9999, we can think of it as 9 plus the infinite series 0.9 plus 0.09 plus 0.009 and so on. We can group the series as 9 plus everything in parentheses, which equals 9 plus 0.9999. This is valid because of the associative property of addition for convergent series. Let's approach this from the perspective of infinite series, which will make the previous proof feel more rigorous. What exactly is 0.999? When we break it down to its fundamental components, we can write 0.999 as the sum of its parts, 910 plus 9100 plus 91000 plus 91000, and so on. Notice the pattern here. Each term has a 9 in the numerator, and the denominators are powers of 10. Using sigma notation, we can write this compactly as the sum from n equals 1 to infinity of 9 over 10 to the n. We can factor out the 9 from each term. This gives us 9 times the sum from n equals 1 to infinity of 1 over 10 to the n. This inner sum is what's called a geometric series. And here's the beautiful thing about geometric series. We have an exact formula for their sum. The formula for the sum of an infinite geometric series with first term a and common ratio r is a over 1 minus r, provided the absolute value of r is less than 1. Our series starts with 110, then 100, then 1000, and so on. The first term a is 1/10. And the common ratio r is also 1/10, since each term is 1/10 of the previous term. Since 110 is less than 1, our series converges, and we can apply the formula. Applying the formula, the sum equals 1/10 divided by 1 minus 1 tar 10. Let's simplify the denominator. 1 minus 110 equals 910. So we have 110 divided by 910. To divide by a fraction, we multiply by its reciprocal. 1/10 times 10, 9. The 10s cancel out. And we get exactly 9. Now substituting back into our original expression, 0.999 equals 9 times 1 9. And 9 times 1, 9 is exactly 1. Once again, we've proven that 0.9999 equals 1 but this time using the rigorous machinery of infinite series. You might wonder, but doesn't a geometric series just approach its limit? This touches on a fundamental point. When we write the sum of an infinite series, we're defining it to be the limit of its partial sums. The equality isn't approximate. It's the precise definition of what the infinite sum means. Let's try a different approach using a fundamental property of real numbers. Suppose, for the sake of argument, that 0.9999 is not equal to 1. If they're not equal, then one must be larger than the other. Since 0.999 starts with 0, it can't be larger than 1. So we must have 0.999 less than 1. Now, here's where real number theory comes in. If 0.999 is truly less than 1, then by the density property of real numbers, there must exist some number x strictly between them. The question is, what could this mysterious number x possibly be? Could x be something like 0.9995? For x to be larger than 0.999, it would need to have a larger digit somewhere. But here's the problem. 0.999 already has a 9 in every decimal place. There's literally no room for x to squeeze in a larger digit anywhere. You might think, what about something like 0.99995? The issue is that 0.9999 means 9s in every decimal place, infinitely. There is no last 9 where we could insert a different digit. Therefore, no such x exists. There is no real number that can fit between 0.999 and 1. This connects to the density property of real numbers. Between any two distinct real numbers, there's always another real number. Since we can't find one, they aren't distinct. Therefore, 0.9999 equals 1. For our final approach, let's use one of mathematics' most powerful tools, proof by contradiction. Assume that 0.999 is not equal to 1. If they're not equal, then there must be some positive difference between them. Let's call this difference epsilon. So epsilon equals 1 minus 0.9999, and it's greater than 0. Now, here's the key insight. 0.9999 is at least as big as any of its finite truncations. 0.999 is at least as big as 0.9, which equals 1 minus 1 times 10. It's also at least as big as 0.99, which equals 1 minus 1 or 100. And it's at least as big as 0.999, which equals 1 minus 1,000. In general, 0.9999 is greater than or equal to 1 minus 1 over 10 to the n for every positive integer n. This means the difference between 1 and 0.9999 is at most 1 over 10 to the n. So epsilon is less than or equal to 1 over 10 to the n for every positive integer n. Think about what this means. Epsilon must be smaller than 110, 100, 1000, 1000, and so on forever. Epsilon is at most 0.1, and also at most 0.01, and also at most 0.01, and so on forever. Here's the crucial question. What positive real number is less than or equal to 1 over 10 to the n for all values of n? None. There is no positive real number that is smaller than every term in the sequence 110, 100, 1,000, because we can always choose n large enough to make 110 smaller than any given positive number. Therefore, epsilon must equal 0. This means 1 minus 0.9999 equals 0, which implies 0.9999 equals 1. Our assumption was wrong, and epsilon must be 0. This proof relies on the Archimedean property of real numbers. Now, let's address the elephant in the room. Some of you might be thinking, these proofs all seem to assume what they're trying to prove. Let's tackle this head-on. One philosophical objection is that decimals are just notation, not the numbers themselves. From this view, asking if 0.999 equals 1 is like asking if 2 equals $. It's about representation, not mathematics. The response is that mathematics studies relationships between well-defined objects. Once we define what 0.9999 means, which we did at the beginning, we can investigate its properties and relationships to other numbers. Another objection: what if we used a different definition for infinite decimals? The answer is that our definition isn't arbitrary. It's the unique way to extend finite decimal arithmetic to infinite cases while preserving all the algebraic properties we expect. If we want infinite decimals to behave like finite ones, if we want 0.5 plus 0.5 to equal 1.0, for example, then the limit definition is forced upon us by consistency requirements. What's beautiful about these multiple proofs is that they each illuminate different aspects of what's really happening here. The resistance many people feel stems from conflating the infinite decimal with the finite approximations we use to compute it. The key insight is that 0.99 is not the process of getting closer to 1. It is the destination. It is 1, written in a different form. Just like how 1, 2, and 0.5 are the same number with different representations, 0.999 and 1 are the same number with different decimal representations. This raises an interesting question. If 0.99 equals 1, doesn't that violate the uniqueness of decimal representations? Well, almost all real numbers have unique decimal representations, but there's a specific exception. Any number that can be written as a terminating decimal also has a representation ending in repeating nines. For example, 0.5 equals 0.4999. 0.25 equals 0.24999. And 1 equals 0.999. This isn't a bug in our number system. It's a feature that emerges from the completeness of the real numbers. So we've seen 5 different proofs, each offering its own perspective on why 0.999 equals 1. Not approximately, not infinitely close, but exactly equal. This equality sits at the intersection of algebra, analysis, and number theory. The next time you encounter something in mathematics that feels impossible, remember 0.9999 equals 1. Sometimes, the most beautiful truths are hiding just beyond the edge of what feels obvious. Thanks for taking this journey into the infinite with me. Thank you for joining me on this journey. If you enjoyed this video, please like and subscribe for more mathematical explorations.